Okay, well, thank you very much, obviously, for everything. It's a great honor to be here and to have I'm very, very honored and happy. So, and thank you for the scientific advisory board. It's hard work, and so thanks for having come up with that solution. I'm really very, very happy. Thank you, Pierre, for your talk. I know it's also hard work to do that, so great. So thank you very much. Thanks for being here. So yeah, I'll try to talk about one part of what Pierre was talking about in his talk, which is the relation between microscopic and macroscopic dynamics. We already heard that in the first talk of the afternoon, so I'm very happy to have the occasion of talking about this, especially in this room called Boltzmann Gasse. I mean, great opportunity to be talking about Boltzmann's equation here. So yes, let me go through little bits of what we've been trying to do with my collaborators, essentially Thierry Bodineau, Laure and Sergio Simonella. So as you all know, a fluid can be a gas, for instance, or a liquid. We'll be looking at gases more specifically here today. So they're made of a gigantic number of particles. Like in this room, the air in this room is made of at least 10 to 24 roughly particles. And they're very, very small, of course, and they move very quickly. And to make things as simple as possible, we're going to say today that they move in straight lines and they collide just by like billiard balls, as Pierre was saying. That means that essentially the equations we're going to write here, Newton's laws, are saying that the position, the derivative of the position is the velocity, and the derivative of the velocity is zero. So there's no exterior force acting on my system. My particles will be as simple as possible, meaning they're hard spheres. So it's not really molecules, it's just identical billiard balls. Their mass is 1. And their diameter, which is very small, is called epsilon here. Okay, so they're going in straight lines, and occasionally, well, actually quite often, they're going to collide. And on collision, the velocity is changed. And the collision rules are given here. You don't have to remember them at all, of course, but all I'm saying here is that they're elastic collisions. The momentum is conserved, the energy is conserved. Okay, and so for notational reasons, we'll call V prime the incoming velocities, and V's will be the outgoing ones that will happen later on. So Newton just writes down those equations. You have a huge number of equations, of course, because X here, which is the center of my hard sphere, is in the whole space, for instance, RD or R3. V is also in RD, or R3 in dimension 3. So you have like 6n equations if n is the number of particles. And they're all coupled. So it's very hard to solve in general. And not only is it very hard to solve, but also you could think it's not really very useful to solve that system of equations, because at our macroscopic level, we don't really care where each particle is at each instant. What we're interested in is, if I open the window, is the wind coming in going to be hot or cold? Is it going to be strong or not strong? So that, of course, is related to the movement of each particle, but the question is, how is it related? That was a question asked by Hilbert in 1900 in his sixth problem. So essentially, his question was, how can you go from the microscopic description of a fluid, which I just wrote, to a macroscopic description? And in between, the dots here say a lot of things, but in particular, he says you could use Mr. Boltzmann's book to help you. And in his book was his equation, and so as not Hilbert, but Pierre was saying, what we're going to discuss mostly today is how to go from the microscopic description to Boltzmann's equation. But before doing that, let me show you Boltzmann's equation again. We saw it first, and also we'll show you the macroscopic equations. So for the moment, we've seen the microscopic equations, and now what Boltzmann suggested, as Pierre explained before, is that you could study, rather than the whole group of n particles, try to project everything into one-dimensional, in some sense, phase space, saying, let me look at how many particles are at x, roughly, at position x, with velocity v at time t. Okay, so x plus dx is density, right? V plus dv. How many particles are there at that time? So this is what we can call a mesoscopic description. It's not yet a macroscopic description. To get the macroscopic description, what you can do is say, I don't really care what the velocity of the particle is. I just want to know the density of my fluid. So I'm going to integrate this quantity against all possible velocities. That will give me a macroscopic density. Okay, I can also integrate this quantity against v dv, where v is the velocity. That will give me a macroscopic velocity. Okay? And then I can also, for instance, integrate against v squared. That will give me some kind of energy or temperature. Okay, so the claim is you have your microscopic description, you hope to have a mesoscopic description thanks to Boltzmann, and you hope that integrating with those moments here, 1, v and v squared, you're going to get some macroscopic quantities, which will satisfy the usual macroscopic equation. So that's the plan, to try to make this work. Here's the Boltzmann equation. So Pierre already showed it to you. I'll describe it briefly as well. So F, remember, is your density of particles. It depends on T, on V, and on X. So the left-hand side is telling you that particles go in straight lines. If the right-hand side was 0, that would mean that every particle is going in a straight line, which is not the case because we know there are collisions, and the collisions are binary. I never talked about more than two particles hitting each other. We could discuss that. In my model, that does not happen. So that's why on the right-hand side, I have a quadratic operator. Okay? And the right-hand side will tell you either you can create a particle, in some sense, it's not really creating a particle, but you can create a particle with velocity v, or you can lose a particle with velocity v. How can that happen? Let's look at this term, for instance. This term is telling you if my particle of velocity v, the same v as here, hits a particle with any velocity w, so I'm integrating against all possible w's, well then, of course, because of the collision, my particle has changed velocity. It's not v anymore. Okay, so I have a minus sign. On the other hand, what can happen is that a particle of velocity w prime, remember I put primes when I'm incoming, hits a particle of velocity v prime, and they're related by the collision rules we saw before. And in doing that, I'm creating a particle of velocity v. The particle is the same. I'm not creating a particle, but I'm creating a particle of velocity v. The velocity has changed. That's why I have a plus sign here. So this is telling you I can gain particles of velocity v, I can lose particles of velocity v. And here I have this extra term, which is known as the cross-section. You see this is 0 when v minus w, that means the relative velocity of my particles, is orthogonal to omega, and omega here is the vector relating the centers of my particles. That happens, there is no collision, actually. Okay, so I'm not proving why this should happen. I'm not proving anything, actually. I'm just presenting you the Boltzmann equation. That's what he suggested. Maxwell as well at the same time, actually. And so I'm just trying to explain that this is reasonable. And the aim of the game is to prove a theorem saying this is the correct equation hidden behind the Newton's dynamics. So this is the Boltzmann equation. And then I told you if you start integrating against 1v or v squared, you should get fluid mechanics equations. How do you do that? Well, here first are the basic fluid mechanics equations you can hope for. So I won't go through them too much because I don't have much time here for this, but if you've never seen them before, you can forget about this. But if you have, you can recognize here the compressible Euler equations. Rho is the density, it's sort of the capital R I showed you before, the integral against dv, sorry. U is the velocity, so it's essentially the integral of f against v dv. And you can also have an incompressible version of the system where we saw that with Pierre before. The second equation here, which is the conservation of momentum, is just divergence of u is 0. That means that the fluid is incompressible. And rho is essentially equal to 1, and this is the incompressible Euler equation. It's the most fundamental, I guess, equation in fluid dynamics. Usually, that's not exactly the equation that's used in practice. In practice, people would usually rely on the Navier-Stokes equation, in which what you've added to the Euler equation is this dissipation term, which we saw again in Pierre's talk. He had taken viscosity here equal to 1. This is the Navier-Stokes system, and then from this system, you can cook up a lot of more general fluid mechanics equations. But the question we'd like to address is how do you go from Newton's equations to, for instance, the Navier-Stokes equation? Maybe using Boltzmann in between. So at least formally, it seems very hard to see that a link between those systems, right? The huge Newton's laws, this PDE. Newton was not a PDE, so the system of ODEs, a lot of ODEs. Now you have a nonlinear PDE in a much smaller phase space. So can you explain how to get from one to the other, at least formally? So the idea Boltzmann suggests is the following. If you want to get the compressible Euler equations, what you should do is rescale time and space in the same way by a parameter alpha. We call that hyperbolic scaling because time and space are rescaled in the same way. So if you change t into alpha t, x into alpha x, you can just get a 1 over alpha here. the rescaling. Actually, from a physical point of view, this alpha is the mean free path. Okay, so the smaller the alpha, the more collisions. Okay, and so now if you look at the moments of F I showed you before, capital R, U, and theta, get about theta maybe for today, take the limit alpha going to 0, compute things, and formally you'll get the compressible Euler equations. Just put to 0 any lower order term in your equations, keep the higher order ones, you'll get compressible Euler. Actually, if you want to keep compressible Navier-Stokes, you would get an alpha Laplacian term. You have the compressible Euler or vanishing viscosity compressible Navier-Stokes. To get the incompressible Navier-Stokes equations, the idea is to use a parabolic scaling, meaning time is rescaled as alpha squared. X is alpha, so that just changes a little bit the powers around here. Again, compute formally what happens, and you get the incompressible Navier-Stokes. Okay, so what I'm telling you here is totally formal. I'm not stating a theorem, but if you can believe me that if you believe Boltzmann, do what I said, and then you get formally compressible Euler or incompressible Navier-Stokes. It works. There are theorems behind that. I won't have time too much at all to talk about those theorems. But what I'd like to discuss more today is how to recover the Boltzmann equation. Okay, let's just pretend, or you believe me, that we know how to go from Boltzmann to fluids, and if you want more, we can talk about that later on. Now, how do you go from particles to Boltzmann? And then we can hope to do both, right? What we want to do is to go from particles to fluids. So what I'm really more interested in today is to go from particles to fluids using the Boltzmann equation. So let's think about that a little bit. So I told you I have a lot of particles. I call n the number of particles. Obviously, I have to have n very, very large. If I only have 2 particles, there's no fluids. Right? So you have to imagine n is going to go to infinity. And as it goes to infinity, the diameter has to go to 0. If not, there'll be a problem in our room. Okay, so there has to be some scaling between n and epsilon. And then I told you to go from Boltzmann to fluids, you have this alpha, the mean free path. I have 3 parameters, and I need to scale them in some way to let n go to infinity, epsilon to 0, alpha to 0, and find fluids. How do I choose the scaling? So that was a computation done by Maxwell, I think, for the first time. What he says was the following. Give yourself 1 particle. Imagine it goes into in a straight line. Okay, remember alpha is the mean free path. What's the relation between alpha, n, and epsilon? Well, essentially, my particle is covering a domain of volume epsilon d minus 1. If t is roughly 1, the velocity is roughly 1, in time 1, right, my particle will have covered an area or a domain of volume epsilon d minus 1. If I want my particle to hit 1 over alpha other particles, how many particles are around me? N minus 1, right? Well, n minus 1 and n are the same. So if I want my particle to hit 1 over alpha, the probability, well, let's say, if I want my particle to hit 1 over alpha others, essentially that means the volume here has to be 1 over alpha. N minus 1 times epsilon d minus 1 must be 1 over alpha. That gives you the probability that my particle will have this kind of mean free path. Okay, I don't know if that's convincing. I hope it is. If you don't like 1 over alpha, take alpha equal to 1 for the moment. Okay, the probability that my particle hits another one will be like n times epsilon d minus 1. Okay, now I want to scale everything up, so I replace the 1 by 1 over alpha. I want a lot of collisions. And that's the correct scaling, actually, if you want to find fluid dynamics. I'm looking at the dilute gas. You see n epsilon d is very, very small, but I have a lot of collisions. So what's known in this situation? Actually, not much. To my knowledge, actually, at least, there's no theorem going from Newton to Navier-Stokes, for instance. In the setting I showed you, the only things that are known, to my knowledge, are when you add noise to the original Newton's dynamics. For instance, you say if 2 particles meet, their velocities will change with some kind of random procedure. Right? If you add noise, then it helps a lot somehow the problem, and you're able to get all kinds of fluid dynamics equations out there. But what we're interested in is not putting any noise originally. You have the deterministic Newton laws. Can we still get Navier-Stokes? Okay? And so I don't think this is, for the moment, nothing is known in that case in general. And so the idea is to say, well, let's try to use Boltzmann. We know Boltzmann goes to fluids, if you believe me on that. Let's prove that Newton goes to Boltzmann, and then we'll be done. Okay, so the idea is the following. I first let the number of particles go to infinity with epsilon going to 0, fixing alpha. Hopefully I get the Boltzmann equation, right? Then I put that 1 over alpha, as I told you before, and then I follow what people tell me that it works, okay, that I can go from Boltzmann to fluids. So what I really had to understand is this limit here, okay, with a fixed alpha. As I said, it's known that Boltzmann's equations go to fluid mechanics in the limit alpha going to 0. There are lots of results. I won't go through those theorems, but there are a lot of results showing how to go from Boltzmann to Navier-Stokes, for instance. So again, I wanted to focus here on how to go from particles. Okay, so just one or two properties on the Boltzmann equation, which are important. So Pierre mentioned the energy for the Navier-Stokes equation. From the point of view of Boltzmann, the energy is the space L log L. You can try that as an exercise. Plug in this quantity in the Boltzmann equation, pretend everything makes sense, okay, which is not so easy, and you'll get this as non-negative, non-positive. This is known as the entropy, right? Actually, it's the mathematical entropy. We all know entropy is supposed to increase. The entropy from a physical point of view is minus F. This is the famous H theorem by Boltzmann, which is actually on his tombstone here in Vienna. That was not exactly this theorem here, but the link between the entropy and the microscopic and macroscopic states is on his tombstone. And this result that he established looking at his equation was a great source of anxiety at the time. Why? Because it was mentioned already in the first talk this afternoon that having something which has a sign here implies that the equation is time irreversible. Whereas the Newton's laws are reversible in time. Just change t into minus t, v into minus v, and nothing changes. Okay, so in the process of deriving Boltzmann's equation, you've lost time reversibility. That looks like a paradox. It's not a paradox once you've understood the proof, but it's a little bit worrying at first sight. It was very much at the time. There are a lot of complaints, for instance, by Schmidt or Poincaré or others. Sorry? Without a T. Sorry about that. Without a D. Yeah, sorry. So as Pierre explained to you, when you have a conserved quantity, or even a quantity is even better, it's decaying in time, you can solve the equation, you can try to solve the equation in that space. You get global solutions, possibly non-unique. That was done in the 80s for Boltzmann. You can also try to solve solutions close to an equilibrium. For Navier-Stokes, it's 0. So near 0, you have global solutions. Here, near Gaussians, you have global solutions, which are smooth and unique. You have the same type of theorems for Boltzmann as for Navier-Stokes. Global, weak solutions in some sense in the entropy space, non-unique possibly. Global, smooth, unique solutions near Gaussians. Or if you're not near a Gaussian, then you have to trade that for locally in time. Now the problem is once you stick in your 1 over alpha in the equation, the local in time becomes alpha, and alpha is going to 0. That's a big problem with Boltzmann, okay, that people had to sort of go beyond to get fluid mechanics, is that if you just look at the Boltzmann equation, rescale time, then the time of existence of your solution is going to 0 with alpha, which is not a good sign if you want to get a limit when alpha goes to 0 of the solution, since it stops living. It's a side remark. Okay, so this is going to be technical. It has to be a part where people suffer. I think now this is where you might suffer a little bit. But I'd like to explain to you what Lanford's theorem is, which Pierre told you about, how you can state it, and a little bit also, again, about fluctuations and largigations at the end. So let me just show you how mathematically you can try to go from Newton's dynamics to the Boltzmann equation. How do you set up things? Now you have to start working a little bit. How do we work? So what you're going to do is look at the set of positions, set of velocities, okay? So you give yourself small n particles. I don't know how many particles I have. So that's one thing that's interesting. Lanford didn't do that. He didn't need to do that. But to do fluctuations, you have to do that. You can't suppose a priori that the number of particles is given. it's an unknown as well, which makes sense, and we don't know exactly how many particles are in the room. We know there are lots, but we don't know exactly how many there are. So n can be anything from 0 to plus infinity, actually. It will satisfy some kind of a Poisson rule. We'll see that later on. So my particles are sitting in a space in which I know they're not allowed to overlap. The distance between the centers of the particles is always larger than epsilon. Okay, so the phase space is a set of all positions and velocities. I call that z, okay, positions, velocities, such that xi minus xj is always larger than epsilon. And now, what can I play with? I can only play with the initial data. Once I know where my particles are initially, then I just let them run by Newton, and I can't do anything anymore. So the only thing I have a hold on is the initial data. And to get the Boltzmann equation, that's what Lanford did, I'm going to assume that the initial data is made of identically distributed particles, okay, following some law, which is F0, which will be the initial data for Boltzmann, hopefully. Okay. So initially, all my particles have this density F0, which is a probability distribution. Okay, so it's a tensorized initial data, up to the fact that they're not allowed to overlap. Okay, so they're a little bit correlated because of that. Okay, and then the number of particles is not fixed again, but it's following some kind of a Poisson distribution. This mu epsilon here is essentially the average number of particles I have. And remember, the average number of particles should be like 1 over epsilon d minus 1. Do you remember that? You remember the alpha before? Alpha is 1 now. I don't care about alpha. Okay, so I had said that n times epsilon d minus 1 had to be equal to 1. That means the number of particles when it was fixed was this number here. Now, the number of particles is not fixed, but the average is this. This is the scaling I choose. So we know that it's called sometimes the Boltzmann grad scaling. So the number of particles is not fixed, but their average is exactly that, because alpha is equal to 1. Now, whenever I take a probability or an expectation, what I mean is with respect to this measure here. Okay, so that's a little bit annoying, but what I have to do is sum over all possible n's, okay, integrate over this measure here, and that's what I call the measure, my probability measure. Okay, this z here is just to make everything a probability measure. Okay. So all you have to remember here is that the number of particles is not fixed, but their average is given by the Boltzmann grad scaling. My particles initially are identically distributed up to the fact that they're not allowed to overlap. And now the question is, where is Boltzmann behind that? This function here depends on n variables, okay, and then n is not even fixed. How can I get a function of one variable, x and v? Well, first thing is, how is this distribution transported in time? That's very easy. It's just free transport, because my particles are going in straight lines, except they're not allowed to overlap. Overlapping means I'm touching the boundary of this domain, which means that this w here, if I touch the boundary, I have to exchange velocities following the scattering laws I gave you at the beginning. Okay, so I have an easy transport equation in a horrible phase space, okay, with this boundary condition given by the scattering. Okay, so now I know exactly everything about my system at time t, and the question is, how do I get Boltzmann? The idea is just to project everything into a one particle phase space. Okay, so the idea, Lanford would have just taken the first marginal because n was fixed. We're looking at a grand canonical formalism, meaning n is not fixed. What I'm going to do here is to integrate all my w's for all possible n's against all variables except for 1. Okay? This is an object which looks like a marginal, if you like, except that I have to sum over all possible number of particles and renormalize for reason. Okay, so this is a quantity I define like this, and the claim is that this guy, which now depends only on x and v, no more x1, xn, v1, vn, this guy is supposed to converge to the solution of the Boltzmann equation. That's the claim. So you could well not like this formula, it's a definition, but if you prefer, there's another way of writing it. I don't know if you prefer it, but this is exactly what Pierre showed us before. It's the empirical distribution, right? This looks like a law of large numbers. 1 over the average number of particles, I sum over all the particles, and I look at a test function computed at the position at time t, xi of t, vi of t. Okay, it's the same. Okay, this formula here which doesn't look so nice, is exactly the same thing as this here. The expectation of the empirical distribution computed at the function h, for any h. That defines a distribution f of one variable. And again, the claim is that this guy converges to the solution of the Boltzmann equation, and that's exactly what Lanford proved, essentially. So what he says is that if your particles are initially identically distributed, as I said before, that means my initial density is what I gave you before, some assumption that I have 0, which I don't have to mention too much, then as the average number of particles goes to infinity, this one particle distribution correlation function, in some sense, converges to the solution of the Boltzmann equation. That's what you wanted to prove, and that's what he proves. So you're very happy about that. That's true for a short time. Okay, and I can tell you right now what the big problem is with this theorem. We'll mention that in a second, but obviously if I start putting alphas in the equation, t becomes alpha t. Okay, so if you can't use this theorem anymore, because when alpha goes to 0, this theorem becomes empty. Okay, so that's why this day we can't go from particles to fluids, is that this theorem breaks down when you stick alpha into the equation. The time of existence, the time of validity of the theorem goes to 0. Okay, he doesn't only prove that, actually in proving the theorem, he actually proves that the n particle correlation function, okay, so now take n configurations, any ones, okay, with some test function, define this as the n particle correlation function, it converges to n copies of the solution of the Boltzmann equation. This comes with the proof, it's actually necessary for the proof, and that's what Boltzmann calls the propagation of chaos. I won't try to say that in German. I won't. I usually try, but not in front of this audience. Okay, propagation of chaos is saying initially my particles were identically distributed and independent. Okay, they all had this F0. As time goes by, they're not independent, obviously, because they're colliding all the time. There's no more independence. But because there are a lot of particles, in the limits where b epsilon goes to infinity, you recover independence. And in the end, the n particle correlation function, as mu epsilon goes to infinity, converges to n copies of f. That's exactly what Boltzmann had assumed. Okay, he said, if I have this property, then this is my equation, and Lanford proves that. Some comments. Why is that theorem true? As I said, particles are not independent because they collide all the time. So to prove that result, you have to say that if two particles collide, at collision time, they are independent. And that's only true if they had not collided before. Or they had not collided with a particle that's collided with a particle that's collided with a particle that collided before. So the drawing Pierre showed you before, you have to eliminate recollisions. You have to prove that asymptotically, when n goes to infinity, when two particles collide, their collision tree were independent before that. Okay, that's really a crucial point of the proof. And actually, once you've understood that, and when you write down the proof in some way, you understand that irreversibility appears just here, because deciding that something is a recollision is saying you have an arrow in time. Right? Because a recollision in one sense is a collision in the other sense in time. Right? So I don't know if that's very clear, but maybe not. But there's a way of stating Lanford's theorem and proving Lanford's theorem, which is really makes it obvious that irreversibility is coded into the statement of the theorem. It wasn't obvious in the previous statement, but actually it is. So there's no issue, no paradox, of course. And so that's interesting. Why is the time short? I mean, maybe Lanford just didn't do things correctly. Why did he get a short time of existence? It's essentially due to the fact that we're looking at collision trees, as I told you sort of before, and it's very hard to control collision trees. And the only reason why this theorem is only a short time theorem is that it's impossible, at least to this day, to control how many collisions one particle will have in finite time. And again, if you rescale time, then you're totally finished. You can't do the hydrodynamical limit. So for the moment, we don't know how to do that. Right, so now what I want to just explain briefly to finish is how could you try to improve this result? So I think that the only way to improve this result really would be to understand, as I wrote here, where entropy is gone. Why? Because the Newton's dynamics are reversible, entropy is conserved, and nothing is dissipated, right? Everything's reversible. Boltzmann's equation, you've projected everything into one-dimensional phase space, you've lost a lot of information, entropy is decreasing. So we need to follow entropy, right, to see where it's gone. And so I don't know if I have time, but maybe there might be a way of understanding that, but for the moment it's totally out of reach. So what we decided to do is to change subject. That's what you usually do in math when you can't solve a problem, just to get another problem. And so what we tried to do is look at much easier settings, which are linear settings in some sense. That's one thing I'll talk about briefly. And then, as Pierre mentioned, we try to turn around around Boltzmann, right? Say, okay, Boltzmann is an approximation. What are fluctuations around Boltzmann? Especially what are large deviations? As I'll try to show you, if you understand large deviations, actually you don't lose any information. Large deviations give you all the information you had initially. And so hopefully, once large deviations are understood, maybe we can go back to Lanford and improve his theorem, maybe. But let me just show you briefly just a bit of an advertisement here about some results that work where you can do the whole program. So Hilbert's program was go from particles to fluids. So it does work in two easy settings. One setting is assume all my particles are at equilibrium except for one of them, or 2 or 3 or 45, a finite number, okay? And then what happens, so I just assume one particle is out of equilibrium, which means I just take one molecule and I move it somewhere else. Then I let it go. What's going to happen is that this particle is going to hit the other ones which were at equilibrium. They're going to be out of equilibrium, but not so many of them. And at the limits of Lanford, you get a linear Boltzmann equation, which is very well known and very easily shown to prove to converge to a heat equation. Okay, and because everything is linear, everything is much simpler in some sense than the Boltzmann equation, we're able actually to do the whole program. We're able to go to the linear equation like Lanford, but then on a time which is not going to 0 with alpha, but actually going to infinity with alpha, which is nice. And so we can do alpha going to 0 here and get the heat equation, and which was interesting in some sense, that this tagged particle in the limits of a large number of particles converges to a Brownian motion. You started with a purely deterministic system, okay, but because there are a lot of particles around you, in the end, this guy satisfied a Brownian motion. Then we did something a little bit more complicated where essentially each particle was a perturbation of an equilibrium. In that case, we were able to recover the easiest model of Navier-Stokes, which is not nonlinear, which is called the Stokes equation, and so that works as well. So those are two examples where you can get the Hilbert's program to work, but of course it's not exactly what you're interested in because everything is linear. So let's change methods a little bit. Just to finish, let me present to you briefly what we've been trying to do regarding fluctuations and large deviations. Pierre explained in his talk that Boltzmann's equation, Lanford's theorem is a law of large numbers. Why is that? Well, if you look at this empirical distribution, which is exactly what I was talking about before, 1 over the average number of particles, sum over all the particles, the Dirac mass at the configuration xivi. Well, you can rephrase Lanford's theorem as follows. I won't prove that, but if you know Lanford statements, it's not very hard to prove that the probability that your empirical distribution computed at some function h is far from its average is, assume this is far, that goes to 0 for any delta. It's exactly a law of numbers, and it's an easy consequence of Lanford's theorem. So then, as we learned before, if you want to go beyond that, what you should do is rescale things a little bit. So define a fluctuation field, where instead of having 1 over mu, you have 1 over square root of mu, which means you multiply everything here by square root of mu. Okay, this is a large guy now. There's no reason for this to go to 0. Okay, so as we saw in the case of Bernoulli variables, this goes to a Gaussian field. And so at time 0, you can compute that easily, and you get that it does converge to a Gaussian white noise. You can compute its variance. And the question is, what happens as time evolves? And so Spohn had conjectured that it did converge to a Gaussian field as time evolves, which satisfies a fluctuating Boltzmann equation. Here it is. That's exactly what Pierre showed us, up to some notation. So I won't go through this. I just want to tell you that his drawing about recollisions happens here. So don't try to read that too much, I guess. I'm sorry, this is a bit technical, but what Spohn said in his book is that fluctuations were related to recollisions. Recollisions were very important. And for a long time, we didn't understand that at all, because for us, recollisions were the enemy. You had to make them go to zero, because recollisions are the problem to get the Boltzmann equation. True, but if you rescale everything by square root of mu, then recollisions appear at first order, and they appear exactly here. Notation, this means essentially a recollision between two particles, 1 and 2. Okay, and this is exactly at the same order as the fluctuation field. And okay, so you can make everything work. You can prove that theorem. You can actually even prove it at equilibrium for as long as you like, for very long times, which allows you to recover fluctuating hydrodynamics, actually, in a linearized setting. And so, okay, so this really explained that his intuition, of course, as always, was totally right. That recollisions are very important at the level of fluctuations. And now to finish, do I still have a minute or two? Let me just finish with large deviations, and maybe a drawing or two, and then we'll be done. So what's a large deviation principle? So it's a very interesting principle. If you've never seen it before, you can't believe something like that could be true. But when you have one, what does it mean? That means that the probability that your empirical distribution looks like, in some sense, I won't explain that too much, a function phi, okay, which is not Boltzmann. So Lanford is telling you this guy looks like Boltzmann, right? The empirical distribution looks like the Boltzmann solution. That's what Boltzmann tells you, Lanford tells you. But now you say, okay, but what's the probability that it doesn't? It looks like something else. Okay, and you say you have a large deviations principle if this probability is exponentially small. Okay, that makes sense because it never happens actually because of Lanford. But exponentially small, it can happen. And you have this universal functional, depending on the time on which you're looking at things and on your function phi. Okay, that's a very nice formula. That's a large deviation principle. And so that happens actually, so in a very restricted setting, so you can't prove anything. But if phi is not too far from f in some sense, then you can prove that, and you can compute explicitly this function f. Okay, so it's, I can't really explain it. It doesn't really make sense at this time to explain what that means, but essentially, if you know large deviation principles, you know that this function here should be some kind of Legendre transformation, which is written here, of some function, which I call here I. Okay, and that happens here. You're happy. And what's interesting is that this function I satisfies a infinite dimensional Hamilton-Jacobi equation, which is very nice, and I'll show you in a second. And I'll stop there, I think. So as Pierre told you, this was known actually, Fredun Rezanhalou had proved that in the case of stochastic particles with a finite number of velocities, so there's a stochastic system, quite different in some sense from Newton's laws, but which still looked like Newton's laws from far, and he had exactly the same theorem. Okay, and so what's interesting here is that you look at the deterministic Newton's equations with all kinds of, with the general system, and you get exactly the same large deviation functional, which he had expected. And actually, Freddy Boucher also recently had expected the same thing. And so it turns out to work. And maybe, okay, can I have a minute or two? Or, yeah? We're all very tired, maybe. I just want to show you one last thing, and then we'll stop. So the way of proving a large deviation principle in general, in finite dimensions, for instance, is to look at this guy here. So you have this empirical distribution multiplied by nu, that's making it very, very large, exponential, expectation, log, and divided by everything. This is called the exponential moment. Okay, if I describe this, I haven't lost any information with this guy here. If I describe this, then I'm able to prove this. I won't explain here. But this is really the good quantity which will give you the large deviation functional. If you believe in the Friedling-Wenzel theorem, that kind of thing. So we believe in that, so we try, and it works. And what you get is that this guy has a limit which solves, and I guess I'll stop here, just I won't want to tire you too much. But I just wanted to show you the Hamilton-Jacobi equation. So this is typically a Hamilton-Jacobi equation in the sense that the time derivative is equal to quadratic functional of your solution. So those are functional derivatives. Okay, and here you have collisions again. in some sense, okay? And this is exactly the formula that Fredun had found in his situation. And okay, so once you have that, well, we're happy we have a reversibility theorem. Maybe just to tell you why I told you, once you have that, actually this guy here gives you all the information in your system. You haven't lost anything. This equation is time reversible. Boltzmann is not. This equation is time reversible. And okay, here I promise I'll stop. One way of writing down this guy is expanding it into cumulants. Cumulants are telling you how particles are correlated in space and time, in time, between 0 and capital T. This f epsilon n is telling you I have n particles at time t. By definition, because of the support of this guy, that's encoded in this formula, okay? By definition, this guy is supported on collision trees that have met in the past. They have to. Okay, that's my construction. That's the definition of a cumulant. Cumulant number 1, f epsilon 1, converges to Boltzmann. Cumulant number 2 converges to, essentially, in some sense, the fluctuation field, limit fluctuation field. Cumulant number 3, I don't know, something else, which also is telling you 3 point correlations. And here you have all the cumulants. And so what I'm saying here is that this formula here has as much information as the original Newton's laws. We know its limits. We know it satisfies the Hamilton-Jacobi equation. So the Hamilton-Jacobi equation has as much information as Newton's law. That we've taken a limit epsilon going to 0. So my belief is that if you want to understand where the entropy is gone, if you want to understand if you can do better than Lanford in terms of a time of existence, then all the information is probably encoded in this Hamilton-Jacobi equation, which we don't know how to solve better than a very, very short time for the moment. But yes, so I guess I've said enough for today. And thank you again very much for being here and for the medal. Thank you very much.
What would you like to about that talk? So, are there any questions? Yes, please. I just wondered why in the viscous case, in the Navier-Stokes case, there's always incompressibility assumed.
Yeah. It doesn't have to be assumed. You can look at the compressible Navier-Stokes. It doesn't make sense. But from the point of view of the particles, you will never, with these scalings, you will never get the compressible Navier-Stokes equations with viscosity 1. The only way to get viscosity 1 is to push time forward by diffusive scaling, and then you get viscosity 1. But if you put diffusive scaling, that means your waves are going very, very fast. So acoustic waves disappear, and you get incompressible equations. It's incompatible to have incompressibility and viscosity, order 1.
So there's a fundamental reason why you don't get this.
Yes, yes. Acoustic waves go away when diffusion appears.
Yeah, many years ago, I learned from Claude Cohen-Danucci and from Jean Dalibard, or your colleagues, about the fantastic concepts of Levy flights.
Yes.
Is my guess correct that if Levy flights would be relevant on the atomic scale, then your derivation would not go through?
I don't know.
Okay.
Yeah, you'd have to explain to me.
Because the concept of averages does not exist. You know, Levy flights are flights where you have local flights and then one big change, and then again, which means that there is no average you can find.
So I might be saying something totally stupid. I wonder if that wouldn't maybe create another model than Boltzmann, of course, where you might have some non-local operators appearing. So I don't know more, so I don't want to say more, but maybe that would happen. But I agree, you wouldn't have something as local, that's for sure.
Is there anything known about other interaction models?
Right, so yeah, more and more. So you can put potentials. If they're compactly supported, everything works the same. It's just a nightmare, but it works. If they're not compactly supported, it's even a worse nightmare. That was done by Nathalie. I think they have to decay very, very quickly in space, like triple exponential, something like that. But it works. Then more recently, people I've looked at what happens if three particles meet at the same time with special scalings. I think Natasha Pavlovich and I forgot. But there has been some work on that. Multi-species, a little bit, it's starting to be looked at as well. The derivation of the Boltzmann equation for a multi-species. Yeah.
And in a relativistic regime?
I don't think so. The equation exists, Boltzmann equation, in that setting, but I don't think the limit has been done in a rigorous way.
Chris. So you said toward the end something along the lines of, to understand where the entropy goes, you have to study the Hamilton-Jacobi equation. Can you say anything more about that? Where does the entropy go, or is that what has been learned about that?
For the moment, absolutely nothing. But the only thing I can say is that if you look at a linearized setting, which is much easier, as I was maybe sort of said before, the L log L becomes L2. In that case, we proved with Laure and Thierry a while ago that essentially the sum of the L2 norms of the cubilants is conserved. We didn't exactly prove that, but I think we could have thought of them differently. So my hope is that in this nonlinear setting, the sum of the L log L norms of the cumulants would be preserved. If this is maybe one totally wrong, and two very difficult. So we've just started trying this a few weeks ago. But if you look at those formulas for the W's and you start putting logs and then expanding everything, and everything gets so messy that nothing is. So maybe it would be better to look at the Hamilton-Jacobi equation from that point of view. But
Last question, Jakob.
Yeah, I've always been amazed how well the Boltzmann equation works, because after all, it is a equation about classical particles and even classical hard-ball particles. But we know, of course, that they are really quantum particles, and the collision time is so short. Even in this short time, if you think of them as localized wave packets in quantum mechanical sense, and even in this short time, these packets will have spread a lot. So why is it not necessary to take that into account, the quantum nature?
Sorry, physicists in the room. I think I have my joker here, but I don't. Okay, I'm going to say something. Yes, I think it's not a question for me. Discuss that maybe. I have no idea. Yeah, there is a quantum Boltzmann. For me, I'm going to say something. I'll just say what I believe. I guess I don't know why you should put quantum effects for Navier-Stokes. I'm sorry if I'm saying something. For me, classical particles, it makes sense for Navier-Stokes. What's more surprising to me is that it works, right? That's true. Especially, I guess when Navier and Stokes put their Laplacian, they had no idea that it was actually the right term to put it in, because it's very heuristic and it does work perfectly. It's surprising. But the quantum, I'm personally less shocked, because I don't think particles at that size would be quantum effects would be so important. But maybe I'm wrong. I seem to be wrong.
Well, they are. If you localize them as a wave
Yes,
packet, and then you choose this collision time, they are already spread.
True, but you have to, maybe the
Spread
scalings are
very
not
rapidly if they are very narrow.
Of course, yeah.
It's a different kinetic equation, like the Wigner distribution function is used in quantum mechanics, and then you derive
Then you get
a similar kind of
similar type of equation. It couldn't be Boltzmann, but you get a transport equation. Yes. If you write down the Wigner transform, of course, you get a transport equation, but you wouldn't get the Boltzmann.
Then you wouldn't worry about Newtonian dynamics anyway, because you would say that's classical.
I think this is a good point to stop. And I thank Isabelle again. The award session we will have.
Before I announce the next piece, I think I can give you a proof, an experimental proof of how the increasing number of the H2O molecules affects our gut streams. Okay, from a 19th century arrangement, the aria Let the Deep Bowl from the oratorio Berchasar by Handel.
I would like to invite all of you to a little reception that we will have now in the common room, and remind you that tomorrow there is some more science. We resume the symposium tomorrow at 9 here in the Boltzmann lecture hall, and now we have some. I hope some more music.
The menuetto of the Divertimento by Haydn. We started at the beginning.